Hello everyone, it is our pleasure to present our ICCV paper, Towards Interpretable Deep Metric Learning with Structural Matching. Recent advances in learning visual similarity are mostly driven by deep metric learning, DIML, which leverages deep neural networks to learn an embedding space where the embedding similarity in this space can meaningfully reflect the semantic similarity between samples. Many efforts have been made recently by either explaining the existing models or modifying models to achieve better interpretability. However, these methods are only designed for explaining the reasoning process of how the output of a deep model is produced and did not consider the interaction between samples, and cannot explain how visual similarity is composed. Now we show the overall framework of the proposed Deep Interpretable Metric Learning, DIML. The feature maps extracted from the backbone CNN model are further fed into the cross-correlation module to compute the marginal distributions. The optimal transport plan is then obtained using the marginal distributions and the similarity matrix. Our framework decomposes the visual similarity to partwise similarities and their contributions, which enable us to interpret and analyze how a deep model distinguishes two images. We start by review the general pipeline of deep metric learning. Formally, given a set of images, deep metric learning introduces a deep neural network that map an image to a feature. The mainstreams of deep metric learning aim to learn Mahalanobis distance metrics. Usually, F can be decomposed into two parts, where F1 extracts a feature map, and GAP is the global average pooling. To exploit the spatial structures in images for more interpretable deep metric learning, we devise a new structural matching scheme to compute feature similarity based on optimal transport theory. Given a source distribution and a target distribution, the minimal cost transport plan can be obtained by minimizing the Wasserstein distance between the two distributions. In the discrete case, the problem can be written in matrix notation and efficiently solved via the Sinkhorn divergence algorithm. Consider two feature maps. We first use the projection layer G to map them into an embedding space of dimension D. The cost matrix can be defined using the distances between the features. The structural similarity of two feature maps can be calculated by the sum of the similarities between the features weighted by the optimal transport plan T star. The definition of the marginal distributions is also important. One trivial solution is to initialize them with uniform distributions, which indicates the similarity of each location has the identical weight to the overall similarity. However, this implies all the features are of equal importance, which is not desired. Instead, we propose to calculate the cross-correlation between the two images. Specifically, we first pool the feature maps to obtain the global features and then slide the global feature of one image on the feature map of the other image to calculate the point-wise correlation. We then discard the negative value of alpha and normalize it to obtain the final marginal distributions. We also propose multi-scale matching to reduce computational costs. In the first scale, we compute the global feature and calculate cosine similarity between the global features as conventional DML methods and find top K candidates. In the second scale, we use the feature maps to compute the structural similarity inside the K candidates. Since K is fixed, the extra computational costs of DIML can be controlled. We can further reduce the computational costs, use ROI aligned to pool the feature maps to smaller sizes. We use H equals W equals G and find G equals 4 can achieve a good trade-off between cost and performance. We can also combine DIML and existing metric learning methods to facilitate training by simply replace the original Euclidean distance with the average of the Euclidean distance and the structural distance. We conduct experiments on three widely used datasets in the image retrieval research field: CUB, CARS, and SOP. We observe that our method can improve performance consistently without any extra training. We also include some ablation studies here. In the top left table, we show the effects of three components. We find combining all three components yields the best performances. The bottom left figure shows that even a small k like 100 will bring considerable improvement. Our proposed DIML is also robust across different embedding sizes, as is shown in the right table. We visualize the marginal distributions, the rescaled optimal transport flow, and the similarity for some pair of spatial locations. We also demonstrate that by re-weighting the similarity matrix S with the optimal transport matrix T, our proposed structural similarity is higher than the standard cosine similarity by a large margin. Thanks for watching this video, and welcome to scan the QR codes below to follow us.